Hello everyone and welcome to this new Weave episode for the STM32 F4 tutorial. And this time this is really special and very important episode because we are going to understand how to manage our program from a memory and performance perspective. And this is sometimes just coming from the right choice of your variable type. So for today's tutorial, first of all, we are going to understand what is the memory size. We are going to deep dive on this. And after that, based on the memory size, based on our declaration, we will see the range of that variable. After that, we see it a lot in many programs. We need to understand, you see, like the uint xx and the bar t. We are going to understand what is this meaning and why we use them. Then the most important and exciting one, taking a look at measuring the performance of your program just by choosing the right variable type that you need to take. And finally, a very important conclusion to wrap up the whole discussion. So let's start first by describing the microcontroller that we are going to use. That's the board, the STM32F4 Discovery, and the MCU or the microcontroller unit is the STM32F407. So let's now take a look to our program. So let's go now to our program and start simulating the program to see what's going on. So let's come here and run the program. So this is our program for today. We do have this program when we declared this this type of variable. So let's make first of all the screen much bigger so you can see it better. So first of all, we declared a char and then a short, then an int, a float, a long variable, and a double. So those variable will be declared and they will have this small value of equal to 2. Just all of them equal to 2, and we will see later on what we are going to do with that. And adding here an unsigned char variable byte size. Just keep for the unsigned, we will understand it later on, but that will be the declaration for today. So what we are going to do now, we are going to use the debug mode and read the value of the size of each variable. So the size of this function is directly from the stdio library, which is a standard library for C. And we are going to read the number of bytes for each variable. But what we would like to read is how many bits we do have. And that's why we multiply by 8. I added the spin value change just to make the program stop so we can read the value each time. So now if we click on the debug mode and move here, so we should be able to stop this. So let's go here, and we do have this dark gray area. So I able to read my variable or the size of the variable type each time. So let's bring it here. So here we do have all our breakpoints here. Okay, that's the maximum I can go, but that's fine. We can live with that. So right now, my variable byte size should be a bit size actually because it's multiplied by 8. We are going to read for the char, my char variable. So if I read here, we do have, and it's reading here, it's only 8 bits. So let's go to the next one of a short. The short have a 16 bits or 2 bytes. Then if I continue reading in the next one, so my integer, this simple int one is having, just let's stop here, we are reading, so we should have, the int should be not 16, should be 32. Let's run it. Yeah, and it becomes 32. So something went wrong, and that's why I put it those pin status change. So now we are reading about the float. So if we go for the float, it's also 32. So the float variables or data size in this compiler for the STM32 is 32 bits. And if we continue here, so this is we still, the long is also 32 bits. So let's now read, let's stop, remove some breakpoint here. So we can stop here. And the long one, these two long, and also the double here is 64 bits. Okay, so you could see that the smallest, from memory perspective, the smallest data size one is the char. So it assigns 8 bits of memory for this variable. When the short is the second smallest one, 16 bits or 2 bytes. And after that, we do have the int, the float, the long. They do have the same data size of 32 bits. Where after that, the long, and the double do have a 64 bits, or more than, I think, 64 should be then 8 byte of memory. I hope I made it correct. Okay, so now we know the size of our memory. We can take a look to what does it mean in other sense. Okay, so let's go and start getting the variable range. So let's go back a little bit here and start understanding what this means. So we do have the signed chart data size is 8 bits, and it goes from, actually we can say from 0 to 1111, or the 0xFF to 0FF. Okay, that's a way of describing the data. And when we put it signed, so if we don't put unsigned or data, we do have 7 bits to describe the value and 1 bit to describe the sign. So if we convert it to a decimal, we will see that the value will be ranging from 127 to minus 127. And each time it's exceeding, it's just going back to the other side. On the other hand, for the unsigned, it goes same, like the value of the number of bits stays same. However, there is no bits for the sign. So all the bits are used for the value. And this gives us, from decimal perspective, a range from 0 to 255 or 255. This is very important because this 8-bit or the char is a really small unit that we can use for memory. So the same logic, you can apply it for all the other member of this data type. And on the other hand, as a conclusion, a small conclusion here, when using your microcontroller with limited memory, the choice of variable is very important. Mostly, if you declare an array of 1000 char, it will cost you 8K bit memory. But if you use a 1000 int, so you say this array have 1000 int, you are using 32K of memory. That's a huge impact. And imagine you declare it as a double. So it's a huge memory that will be consumed and can generate some issue to your microcontroller. Okay, so now let's go to another type. Now that we understand the size of the chart, the data type, let's go to the understanding this always u int t xx and a bar t. So we do have this kind of picture. The u, this one means unsigned. The int is just to describe it's an integer, and the xx that you see is the number of bits. Continuing in this logic, simply the int8 is a signed integer with 8 bits, and then the int16 is the signed integer with 16 bits, and it's a short, and the int32 is the signed integer with 32 bits. And after that, using the same logic, by adding the u, we do have the same logic to create those memory. But the question comes here. We do already have the char, the short, the int, and unsigned char. Why do we need this kind of int8t? This is because the definition of char may change from a microcontroller to another, from a C compiler to another. So some compiler will say, no, I have a huge supercomputing power, so and my microprocessor can manage 36 bits in one row, this means my char is 32 bits. To make it standardized, you can create this int 8 and int 16 to say I'll be using as a minimum, I will have in this variable on within this declaration a minimum of 8 bits, a minimum of 16 bits. Doesn't mean it will have more, it can mean it have more than that number of memory, but at least the number of bits that you're assigning. Okay, that was how we understand this int, this uint, because many people sometimes get confused with this writing, and it just the declaration of the variable. Then let's go to the most exciting part of this program, and this is regarding measuring the performance and how we are going to do so. So let me go back again quickly to the picture of the video here. So we do have our microcontroller connected with this logic analyzer, and we are going to perform a loop of a very simple operations for each one of the variable and measure the time that it would take. And we will see together now the program that will do that, and then we are going to read it and see the simple operation for the same number but with different data type, how much it will impact the performance of the microcontroller. So let me show you now the code again. So let's go here. So we can leave the mode, the debug mode, because we want the microcontroller running without any problem. And so what we do have here, so we start here, we created few pins here, so kind of defined some pins from PA0 to PA7. So we are going to use the PA0 as a start pin to start the evaluation of all the pins. So that will be our range of all the evaluation. And then we will have a pin assigned to each one of the data type. Now let me explain further the logic. So each time we are going to run or to set our pin high before starting the loop. So we are going to start a loop, and it will be 100-time loop. Within this loop, the variable will be equal to the variable itself multiplied by 100, and then the variable will be equal to itself divided by 100. So the value of the variable will not be changing. We're just going to perform 100 times a multiplication operation and a division operation. And this will happen for each one of them. And when the operation will finish, we are going to set up our pin low. So we just kind of put the operation here. The time for to set a pin high and low is the same for all the pins. So there's no difference there. The only difference we do have is how much time this kind of operation will take time. So we are going to set up the char pin, the short pin, the int pin, and after that the float pin, and after the float pin, the long pin, the long pin, and finally, after the long pin, we do have the double pin. So we will check the operation for all of them. And to need that, as I said, we have a logic analyzer. So let me bring the logic analyzer quickly. Okay. This is the logic analyzer. Let me bring it. Somehow it crashed. So apologies. Let's do yes again, and sorry. Okay, and here it's restarted. Well, okay, so this is our logic analyzer, and now you see we do have all this column. Each one of them will be reading the state of the pin. So we do have, this is the period when we are starting the operation and ending, so we can control that. And after that, we do have the char pin, the short pin, the int pin, float pin, long pin, and the double pin. Okay, so without waiting further, let's run, and we start seeing some really nice pictures. So now we are in a reading mode. We are reading the data, and let's stop here to see the result. So as I said, the period pin is by when. So let me go show you the code the last time. So if I squeeze everything, this pin start high when I start all the loops here, and then it will go low when I finish everything. So by having this, I can know this is the whole time it took to make every operation one by one. And it took me almost 2 milliseconds. Let's start with the char. The char is taking 45, let's say 49 milliseconds to perform that operation. The number here that we do have, and I repeat again because it may be a little bit confusing. So we do have 2 for the char, and I used unsigned so I can multiply by 100. So if I multiply the 2 by 100 and divide it again by 100 times, my microcontroller need 45 microseconds to perform this operation. And we said the char is only 8 bits of memory. After that, we do have the short. The short takes 51 microseconds to perform the same operation that the char took 45 microseconds. And the short is 16 bits of memory. Then comes the int. The int, surprisingly, which is a 32 bits of memory, takes less time, not that significant less time than the char, but it's more performant. On the other hand, from float perspective, it takes 108, almost 109 microsecond to perform the same thing as an int. So you see here the int is taking 40 seconds and the float is taking 110. So it's almost 2.4 times the time that is needed for the int to be performed. Then we go to the long. As we have seen previously, the longs have the same size as the int, 32 bits. It takes almost the same time. So it's 39.8, where the int is 39.7. It's same. So if we check it again, here it's 39.75, 39.75. It's really almost the same time. Same here for the float. It's 108. So the float also is a 32 bits of memory, but because of the composure of the float, the float, and it has the gamma, it requires further computation, and within the even we are using the same number. Then comes the long. The long takes 673 microseconds to perform exactly the same operation that it took 40 microseconds to do. So here we are talking at least 15 times performance. So just to be careful about that. Finally, we do have the double. So you see here by the double takes 873. So it's 22% less effective than using the int. That's quite interesting how the data structure and how the compiler manage the data, how much it's impacting the performance. So seeing all of this, you would understand that you should always, if you don't need them, the long and the double should not be used in your program. They are really consuming a lot of memory, and most importantly, they are not efficient compared to the int. Okay, so now, just for sake, let's compare one thing. So I see a lot of people when using, they are trying to use the ADC, trying to use always the gamma. They wanted to know how many millivolt they do have. So for this sake, I changed this program. So I will comment everything here. Let me make it small so I can comment. I will explain the new code that I do have. So let's comment this one here. Let's comment here and bring this pin here. So uncomment another part of the code that we are going to use now. So let's bring it here. And this code, let's say, instead of using like this is the float variable, my float variable, and the value of my voltage is 1.253 millivolt. On the other hand, if I put it, sorry, this is a volt, 1.253 volt, or I can read it as 1,253 millivolt. And we are going to perform almost the same thing, but here in my loop, I'm intensifying the loop to see how much performance we are getting or losing just by using the difference of these two ones. So we are going to perform the same thing, a loop of 1,000 times, multiplying here by 1,000, dividing by 1,000, and same for the float variable. So let me save and build the code and load it. So only now the two pins, the int pin and float pin, will be working. So let me bring back the logic analyzer and run it again. Let's run it a bit, and we can see now we do have this picture. So let me try to make this one a little bit bigger, and this one because only the float is working. So we are going to count only the time when the int is high. So that's the computation that we need. So we spent 377 microseconds to do the operation. So 1,000 times multiplying by 1,000 and dividing by 1,000. On the other hand, the same value, the 1.253, took 1 millisecond, a whole 1 millisecond to make the same thing. So you can see if you manage some data that in casually is used in a certain value with a float, and if you are seeking performance, it would be more interesting to use it as an int with a bigger integer value to get more performance against what's going on. And this is happening more if you do some regulation program and you need a very quick response from your system. The int can be quite a very good option to do that. So that was the part of measuring the performance. I really enjoyed doing this analysis. I understand really how this is working. Let's have our conclusion and wrap up. So first of all, your choice of the variable will influence a lot the use of memory and performance of your microcontroller. The second one, we found out that integer and long data type are the most efficient. They do have the same value of bits in their memory, at least for the STM32F4. Also, long and double are more time and energy consuming data types. Finally, try as much as possible to use integer data type instead of float, as they are more efficient. Then this is my final personal conclusion. So if you still use double or need to use double or long variable type, just go work for NASA. Yeah, because they probably need you. Okay? So thank you so much. Really appreciate you following this episode until the end and wish you a fantastic day. Bye-bye.